This is the third video on section 7.4, double integrals with polar coordinates. So here we're going to start by looking at theorem 215. Now, in the previous examples we looked at, R was bounded between A and B, theta was bounded between alpha and beta. The idea behind theorem 215, however, is theta is still bounded between alpha and beta, and we want beta to be less than or equal to alpha plus 2 pi, so we don't want to go around the circle more than once. R, however, isn't bounded between two constants. R is bounded between two functions of theta. So h1 of theta is less than or equal to R, which is less than or equal to h2 of theta. Now that's not to say that one of these functions can't be constant, but this is the situation we have. R is bounded between two functions instead of two constants. In this case, integrating over the region, f of x, y, dA is similar to what it was before. We have f of r cosine theta, r sine theta, r dr d theta. That's what we're integrating. The r limits of integration now, however, go from h1 of theta to h2 of theta instead of simply from a to b. Theta still ranges from alpha to beta. So this is similar to, say, a type 1 or a type 2 region in rectangular coordinates, except we're using polar coordinates here. And so, example 216, we want to find the area of one loop of the 8-leaf rows, r equals sine of 4 theta. That's what the problem says. I didn't write the problem on the board here, but that is the problem from your notes. We're going to do an area problem by making it a volume problem, okay? So the volume of the region whose base is the one leaf of the rows and whose height is 1, that's just going to be, so the volume of that, so imagine this has height 1. The volume of that region is the same as the area of the base. And so we're going to calculate the area by calculating a volume. We're going to calculate the volume with a double integral. But the function that we're going to use to integrate is simply the constant function 1. That's what we're doing here. So the region we're looking at is a set of points r theta, where theta is between 0 and pi over 4, because we're only looking at one loop at one leaf of the rows, and r goes from 0 to, well, this function of theta, sine of 4 theta. So we're going to integrate over that region 1 dA. And I've explained why we're integrating the constant function 1. Because the area of the region that we want and the volume of this region with that base of height 1 is the same. So we're going to calculate an area by calculating a volume. And so then we have, again, we're integrating our function 1 times r dr d theta. So we have 1 times r dr d theta. Again, that's what we're integrating, right? F of r cosine theta, r sine theta, r dr d theta. For this particular example that we're looking at, our function is the constant function 1. So we have r1, then we have 1 times r dr d theta. The r limits of integration, 0 to sine of 4 theta. The theta limits of integration, 0 to pi over 4. So now that we have this, you could probably finish this, but let's go ahead and do this. So we find an antiderivative with respect to r, 1/2 r squared, substitute the r limits of integration and subtract. And now we have the integral from 0 to pi over 4 of 1/2 sine squared of 4 theta d theta. This is a calculus 2 problem. We use a trig identity, so I factored out a 1/2. And then sine squared 4 theta is 1/2 times 1 minus cosine of 8 theta. That's a trig identity that we learned in calculus 2 and probably also pre-calculus. Factored out a 1/2 again, that's where the 1/4 comes from. And now we'll just find an antiderivative of 1 minus cosine of 8 theta. That's actually a calculus 1 problem. So an antiderivative of 1 is theta. Antiderivative of cosine of 8 theta is 1/8 sine of 8 theta. We're subtracting. So we have this antiderivative. substitute pi over 4, substitute 0, and subtract.